if I give you a graph and I ask you partition the graph into partition it into two sets, partition the vertices into two sets, so that the number of edges going from one set to the other is maximum. Or in other words, give me a two coloring of the graph which has a maximum number of edges between them. Or give me a bipartite subgraph of this graph which has the maximum number of edges. So, if you look at it, the number of edges, which for of course you could also generalize this further. There's also something called a weighted max cut, where instead of counting number of edges, you will just add the weights. But in either way, you can see this is a submodular relationship, because every time I add a new vertex to this set of blue vertices, I'm going to be doing two things. I'm going to be adding edges from this new vertex to these two guys, for example, right? That means the complementary set of this new guy. Imagine that I put J with the blue now. So I'm going to be adding edges from J to these two guys, which means one, and then that's exactly this one guy, that's it, right? That's the addition compared to what was already there. But I'm also going to be subtracting something, which is basically the edges from J to these blue guys. So for example, these two which I'm pointing to here was earlier in your cut, but now it will not be in the cut because now J has been added. But the point is that because of this S being, so if you look at the definition of submodularity, we needed that S should be strictly contained in T. So because of that condition, adding J to a smaller set has to give you a larger incremental value than it does to a larger set, because of this property that S is contained in T. So this is one example of submodularity. Another interesting example is influence maximization. So nowadays, we have these social media studies going on, where people try to understand how much influence a particular set of users have on in terms of like spreading rumors or spreading good things as well. So this is a big field of study, but essentially, to cut it short, here we are looking at average number of nodes reachable from a seed set S. So earlier here, for example, we were looking at it deterministically. Here there is a certain chance that, for example, I can influence J with the probability whatever, Pij. So there's a chance that it can be influenced. So therefore we are looking at, in expectation, the number of nodes reachable from these blue colored nodes are basically, it's a submodular function. And why is that? Again, because of similar reason, because expectation preserves the submodularity, and then the rest of it you can understand from the same logic as for the cut capacitor. Similarly,
first example.
Yes.
So when we add a new element.
Yes.
Where? So you have the graph and you have already colored it, right?
Yes. Correct.
Then I bring a new element.
Yes. So for example, you put J. So now you had, this was your S, for example. So you look at this guy here, S, and then there is N. Remove S. That means the complementary set. So this was S, and this was the complementary set. Now assume, for example, that I put J in S.
Okay. I'm just looking at the set N. The N is the total.
N is exactly. N is the whole number of vertices.
Okay.
Not adding any new.
Not adding any
nodes.
No. Okay. So max cut means you just give me partitions. You give me a partition, I'll tell you what's the number of edges crossing from one to the other. You give me another, I'll get another set. So I want to find the partition which maximizes the cut. That's the goal, right? So this is actually an NP-complete problem. This is not an easy problem. It's known to be, the decision version of this is NP-complete, and the optimization version of this is the NP-hard, the max cut problem, right? So anyway, so this also now, interestingly, since you asked, so you can see this is a submodular function, right? And we know this is already NP-complete. So essentially, it kind of points also to the fact that maximizing submodular functions is not easy, and which we will come to slightly later. On the contrary, minimizing submodular functions is easy for many cases, most of the cases actually. Anyway, so sorry, I'll just complete this. Entropy is also a submodular function, and this is another interesting example where if you just take the maximum of, let's say, n costs, you can see that this is submodular, because if you add, so if you imagine you have a set S, and then you add the n plus 1th guy to this guy, versus adding him to only the blue guys. Imagine there's a Cn plus 1. Adding Cn plus 1 to C1, C2, C3 is more beneficial than adding it to the whole set, simply because if Cn plus 1 was the maximum, then anyway it would be the maximum of both the sets. And you would actually, and we know for sure that the maximum of the whole guy must be great, at least the maximum of the blue guys. So therefore, this is a submodular function again. So now this is interesting because the expected value of this function is nothing but the union probability. So if you see, like if you take the expectation of this function, you'll exactly get back the probability that at least one event happens, right? So anyway, so these all, the point is all of these have motivations. They're actually arisen from motivations in, for example, facility location, incapacitated facility location problems, and in many other applications that have been used. For example, even in sensor location, for example. So if you want to place sensors in such a way that you maximize the area covered by them, so that function which measures the area covered by these sensors is also a submodular function, because when you add a sensor to already many more sensors than, let's say, a subset of it, you cover lesser incremental area than what you would have if it was a smaller set. So like this, there are many others, but let me come to the optimization part. What is the goal of the literature till now? It has been to actually maximize or minimize f of s, where f of s is a submodular function, and s basically lies in a set of what I over here represent independent sets. And m here basically it forms, you can think of it as basically maximizing a submodular function subject to a matroid constraint. Now what are matroids? Matroids are basically, you can think of them as sets of subsets of this power set here, for example. So 2 raised to 1 is a power set. So you're given certain sets of subsets which satisfy some constraints. For example, it could be a cardinality constraint. So the simplest matroid you could think of is, where the cardinality has an upper bound. That means you can have only sets of at max, let's say, some k cardinality. So in this case, this kind of optimization is called deterministic submodular optimization. Now, minimization, as I mentioned a few slides ago, is easy. The reason is there's something called Lowa's extension. So I'm not going into the details of this, but if you're interested, you could read it. So basically, you make it a continuous extension. So you go from the discrete space to the continuous space, and then you get the minimizer of that Lowa's extension, and you convert it back to a minimizer of the original discrete space. So these are the ideas in the literature, but maximization is hard, and for reasons we have.
When you say easy, what do you mean?
So easy means it can be solved in polynomial time. Yeah, because
get the optimal solution.
Yes, because this Lowa's extension, it can be easily solved in. So it's a linear program. It can be solved in polynomial time, and then converting it back is also possible in polynomial.
Sort of rounding.
Yes, exactly. So there is a rounding there. That's also possible. Whereas in the case of maximization, unfortunately, what happens is that the extension. So the reason why Lowa's extension works is that, again, it's convex. You see, it's convex. So we can't use it for maximization. So for minimization it works. Whereas there are other extensions which have been designed which unfortunately are not concave. Getting concave extensions has proved to be a bit difficult, because of which maximization, and of course the problem is hard by nature. It has been shown to be hard. So therefore all kinds of approximations have been obtained in the literature. For example, like there's a 1 minus 1 by E approximation for uniform matroids using the discrete 3D algorithm. This is all seminal work way back. And recently, that 1 minus 1 by approximation was extended even to general matroids. So general matroids is a harder problem, and this is with the continuous 3D algorithm and rounding again. So these are some techniques which have been used. But the reason I'm just mentioning this briefly is because, number one, all of these have this assumption of monotone submodular functions. Otherwise, it doesn't work. So there is need of both of these properties, monotonicity and submodularity. So in general, these type of combinatorial optimization problems are hard problems, because you're essentially going to have many subsets. You can't enumeratively solve it. But because of submodularity, we are able to get these approximations. That's the point which I want to make. So the crucial point is submodularity buys us something which is actually it's people say it's a discrete analog of concavity, because of the way of convexity, because it's easily minimizable. but it also has a lot of similarity to concave functions. Because just the law of diminishing returns, if you look at it, it's aping the concave functions. Whereas, as far as behavior is concerned, it's behaving more like convex functions because it can be easily minimized. So, it's hard to say which it apes, but the point is, it has very interesting properties which is making life easy. That's the point. Now, in my research, it has not been what the literature has been looking at. There's a slight difference because my goal has been to look at the behavior of submodular functions under randomness. So whereas what I showed you in the previous slide, in this case, f of s is, so here everything is deterministic, right? So you just give me a set of subsets and then I optimize over it. Now I'm introducing an additional layer of complexity, which is the randomness. So the S itself is random because I choose a set with a certain probability. Earlier I was choosing a set, it was deterministic, right? If I choose this is the value, and then I keep doing that, I get the maximum value. So now we want to solve problems in expectation like this. Right? So the maximum over some distribution, set of joint distributions of the expected value of the submodular function. Right? And of course, the joint distribution will have to satisfy some marginal probabilities and some correlation structure, which we will discuss later. But the assumption of monotonicity remains the same. We need it here as well. Right. And one more thing, I think I didn't mention that, oracle access. So in all of these problems, whether it's a deterministic or in our study, we need oracle access to the submodular function, which means you give me an S, the oracle, whatever, the God-given oracle will be able to say that this is the value of S. And yeah.
Joint distribution over what?
So okay, joint distribution over the S. For example, S, right? So S is a set, right? Now each element of the set is chosen with a certain probability, and the joint distribution obeys certain correlation, right? So for example, the probability that, let's say, 1, 2, 3 is chosen, right? So that is one scenario in the, out of the 2 raised to n power possibilities, exponential possible scenarios. So that's why it's a joint distribution over the S's, basically.
Over the S you are saying, see, because, so basically there are n items, right?
Yes.
So given any subset of item, you are telling there is a probability. Is that what you are saying?
Yeah, so exactly. So basically, you have n items.
Yeah.
Okay, so there is a certain, okay, now each of those items have a certain probability of occurring.
So that is the marginal
That's
probability.
a marginal probability.
Okay.
Okay, now, as far as the joint is concerned, there are many ways we can do it. Now, suppose you don't tell me anything more than the joint, the marginal probabilities. Nothing more. I only know the marginals. Then what I do is I can create many possible joint distributions with joint distribution meaning like, okay, the
Over the set, over the all n elements.
Yes, over the n elements, where each possibility will take a certain probability, but satisfying these margins. Now, if I say, no, I'll give you more information. I'll give you bivariate information. That's what we are going to discuss, pairwise independence. Then it becomes a little more, okay, then I'll have lesser number of distributions, but it's still not like completely independent.
Just to understand it further, so there's a chance, non-zero probability that you can pick all the elements.
Yes,
Distribution.
yes, there is a non-zero
But
probability.
push it
typically you
down.
have a cardinality constraint on S, right? So
Yes, exactly. Okay, so uniform method, which is exactly what you're saying. You have a cardinality constraint.
Correct.
Here, we are not optimizing over the set of subsets. Rather, we are just optimizing over the set of distributions. So it becomes a DRO submodular optimization. Right? So therefore, we don't, actually we can have cardinality constraints. It's not, but it's just
So
that.
you can indirectly impose it on the distribution itself, right?
Exactly, we could. But the point is, even this is hard enough. So, we will see now, for example, these problems are, you can approximate them, but it's very hard to compute them exactly. So, if we add it, yeah, I mean, probably there could be results out there. That's a good point, actually. We could. Yeah, but yes, joint distribution is over these possibilities, right? So, there are 2 raised to n possibilities if you consider the whole ground set, and joint distribution is over that. Okay, now let me, I think I'll be, maybe you can stop me with the time.
Yeah, we have 15 minutes more.
Yeah. So, the pairwise independence concept is something critical for our research. So I'll just quickly go through it. But it's interesting, pairwise independence, so if you look at this last point here, this is essence of what I want to say. Mutual independence implies pairwise independence, whereas the converse is not true. Okay, so we all know what is mutually independent, right? So mutually independent means basically the probability that n variables take these values is the product of the marginal probabilities. But then this is assuming a lot. Why? Because every time you add a variable here, suppose I put a Cn plus 1 here, you are actually freezing the joint distribution. Because you don't give it a freedom to to the joint distribution. The joint distribution is fixed. If you add another variable, then you're just going to multiply the last probability here. Whereas with pairwise independence, that's not the case because you're only looking at pairs, and all that you're imposing is that they have the probability, the joint probability that Ci equal to 1, Cj equal to 1 is the product of the marginals. So now this gives you a lot more freedom because you're not adding so much information. But what's the trade-off? The trade-off is you deal with much more complexity because now you can have so many possible distributions which satisfy this, right? But the good point is you're going to get better results because you're assuming less. You're not freezing the joint distribution. For example, the bounds would improve. Bounds on expectation or probability function would improve. Anyway, so the even bigger question which I just want to briefly motivate is why do we even look at pairwise independence? Because in nature, we do see that there can be close to zero correlations between variables, random variables, but there could be higher order dependencies. So correlation is measured between two random variables, whereas for 3 or more random variables, you could have dependencies, right? So that means, whereas for the mutual independence case, we didn't have higher order dependencies at all. It was completely frozen. So here, for example, in this paper, it's quite a famous paper by Sneedman et al. In Nature. So what they show is when you look at the retina, the vertebrate retina in our eyes, so there are these neurons carrying the information, and it is observed that these neurons behave in a way that for pairs of neurons, they exhibit close to zero correlation. You can see the histogram here. It's almost close to zero for pairs of neurons. But then when you look at the probabilities, so if you assumed independence, you would get this line, this blue line here. But the reality, what is observed is much different. Now you can see the probabilities are higher. So for a given number of spiking cells, you can see that the observed probability is higher. The reason being, it's in practice there is higher order dependencies. Whereas here we are assuming too much, and therefore the probabilities are less. So this is one of the reasons we might be interested in pairwise independence, other than the mathematical part of it. Right? I'm going to just talk about it a little more. So the best, I would say, the motivating reason, as far as I can see, of pairwise independence is that it allows for low cardinality. Right? So here, for example, you see here, this is a joint distribution where all the probabilities add up to 1. They satisfy the marginals, and this is the pairwise independence constraint. Right? So here it's xi, xj. Xi and xj are basically the probabilities, the marginals. So now you can see that this, if you look at the number of constraints, it's just order n square constraints. Right? Because here you're going to have n choose 2 constraints, here you're going to have n, here you're going to have 1. So earlier, for mutual independence, you would have had 2 raised to n constraints. Now you have this order n square, which basically means you're going to have many more possible distributions, but the bounds will be better. Okay. Anyway, so these are some technical results. So as I mentioned, n choose 2, n choose 1, etc. But where has it been used in computer science? It has been used, for example, in de-randomizing algorithms. For example, the max cut, the same max cut which we talked about. Now, if you were to solve it, so typically, it's an NP-hard problem, but there are approximations. So the simplest approximation is the half approximation. So you just take 2 vertices, flip a coin, and randomly decide, which color to give to these 2. Actually, do it for all the vertices, flip a coin and decide which color to give. But you do it independently. That means they are all independently chosen, the colors. Now, if you do that, you can guarantee that at least half the number of edges will be chosen in expectation. Why? Because, if you take 2 vertices, then there's a probability half that, they will be of different colors, right? Because 1 by 4 plus 1 by 4. So either, let's say, blue, blue, and red, red. So it's half into half plus half into half. So you're going to guarantee half the number of edges in expectation. But the point is you don't need that. You only need pairwise independence because all that you need is the pairs of vertices should be independent of each other, right? So now imagine if you have a distribution of this type, just order n square. I don't have to count exponential number of points. I just go through each one of them. For each one of them will give me a coloring, right? A partition. I'm guaranteed that I'll be able to get that same approximation by counting these n square possibilities, or n square possibilities. So essentially, this is de-randomization in action for pairwise independence. And the other thing is, it's also the gateway to correlated distributions. For example, positively correlated, negatively correlated. All of these are larger classes of functions, which include pairwise independence, right? Because positively correlated is greater than or equal to instead of equal to, negative is less than or equal to, and then they could be mixed also. Some subset of variables are positively correlated, some are negatively correlated, and they could be independent, etc., etc. The point is, pairwise independence can be giving intuition to deal with these class of problems as well. So just as an example, you can see, just take 3 variables with probability half, half, half. You can see that there are 3 possible distributions. This is the mutually independent distribution, and these are 2 pairwise independent distributions. You can verify this easily, that these are, maybe not now, but it's a standard example. So the point is, you can see that already with 3 variables, we are able to halve the support space, right, from 8 to 4. So just a graphical visualization of this. So here you can see what I showed you in the previous slide. So these are what is in red is your basically sets. So if you include element 2, then the probability is 1 by 4, element 1, 1 by 4, 1, 2, 3, 1 by 4, etc. Now if you look at the second distribution, it's the flip of the first distribution, and this is pairwise independent, and this is the mutually independent. So you can see that the low cardinality is there, and any convex combination of these distributions is also pairwise independent. So you can literally get infinite possible distributions which are pairwise independent. So our goal was to understand the behavior of submodular functions under these weaker notions of independence, because pairwise independence is a weaker notion of independence, right? Simply because we are not imposing so much information. So anyway, traditionally this has been the approach: go from the discrete space to the continuous space. So like here, you have these points. Now you say, okay, I will instead maximize an extension which captures this hypercube within these same points, which is basically the convex hull of these points. So I will now look at this convex hull and I will maximize that same, but not the same function, but the extension within this cube, within this hypercube. So
this is that Lova's extension.
This is the, okay. So Lova's is one of the possible extension which uses this idea. But there is another one which is known as multilinear extension. So multilinear extension is
basically making the variable 0, whatever, continuous between 0 and 1.
Exactly. So basically that means what it does is, it takes this guy, okay, so it takes the function value at these points, and then so for example here I am including 1, 2, but 3 is not there. So all that it does is, if 1 and 2 are included, it will multiply with x1, x2, and 1 minus x3. And similarly, it will go to the next point. It will only take those points which are included, and then multiply with the complementary properties. So that's the multilinear extension. Expected value of the function where element I is selected with probability xi independent. That's the crucial point. Independent. It's not here we're talking about complete independence, right? So this is how mathematically we write it. And then there is this concave closure, which is again crucial for our discussion today, where instead of now looking at this kind of independent distribution, I don't in the concave closure, I'm not going to say that they are independent. I'm just going to satisfy the marginals, as we discussed earlier as well. So now, this is nothing but the expected value of the submodular function, but now I'm maximizing over the set of joint distributions, right? So here there's nothing to maximize because this theta ind is frozen. There's nothing to maximize here. It's just one distribution. But here, we need to maximize because there is many possibilities. Now, why would we look at this concave closure? Because unfortunately, this multilinear extension is not concave. As you can see, it's not concave in the x vector, the probabilities. It can be shown to be concave in some directions, but not always. Whereas this guy is concave in theta because it's just linear function in theta. So it has some advantages because of which it also has been studied.
But you not perturb it to make it convex.
Sorry?
For example, the first equation,
yes,
f of s,
yes,
you not perturb it so that it becomes concave or convex, but when you substitute discrete values or whatever,
yes,
1, 0, it will be 0. So perturbation is good in that sense.
Yes, yeah. So when you substitute discrete values, exactly, you will get back. So for the indicator function, you will actually get back your f of s. So for example, if you say indicator s, where it's only so it's like f of this guy x. If I put x equal to 1 s, which means indicator s, then you'll actually get back f of s, right? But then but whether you can perturb and get convexity could be possible.
I think it's possible, but the question is it a good approximation?
Good approximation.
That depends on probably.
Yeah. I think anyway there are results which say that you can't go better than 1 minus 1 by e. Meaning without exponential number of queries, you cannot do better than 1 minus 1 by e. So actually the bound which I showed you earlier is a tight bound. So I think people are at best trying to reach that 1 minus 1 by e path. Because even that has not been reached for all classes of functions. Yeah, so anyways, okay, now I'll just quickly talk about this notion of correlation gap. So I showed you this convex closure in the numerator, and this denominator here is the multilinear extension. So essentially this ratio of these two has been shown to be bounded by e minus 1. So in other words, basically what this says is that you can get a 1 minus 1 by e approximation for this, for this f plus of x, right? So you just take f of x to the other side, you get f of x at least 1 minus 1 by e times of f plus of x, because f plus of x is known to be NP hard to compute. The one which I showed you, the concave closure, is actually known to be NP hard to compute. It can be shown that it's equivalent to a max cut problem, which earlier we discussed. So by reduction from the max cut problem, it's also NP hard. But anyway, the point is, we can do as good as 1 minus 1 by e. This was shown by Shipra. Now, our results are, instead of this denominator capital F of x, where we use complete independence, what happens if we use pairwise independence? That's in just the focus of my work.
Can you just go back to the previous thing?
Sure, yeah.
Previous slide, no.
Before this, yeah.
So the first one is fully independent, no? The
Exactly.
objective function is computed as a...
Exactly. Expected value of the submodular function under independence.
Now when you are trying to maximize over all possible independent distributions?
No,
means
here it's not independent because I'm only enforcing that the marginals are satisfied. So this is known as worst case correlation model, which
Okay.
means it's like the other end, exactly the opposite end of independence. So you have complete independence and then you have complete dependence.
Yeah, it can be arbitrarily correlated, but the marginal should match. That's what
Exactly.
you're.
So it could be positively correlated, it could be negatively correlated, it could be pairwise independent. So this is actually the largest class of possible distributions, because you're going to have the independence is the most restrictive. Pairwise independence is a little less restrictive, and then positively, negatively correlated, even less restrictive. And this is the least restrictive, right? So this is the other end of the spectrum. So actually, okay, good. Thanks for asking this, Professor, because the whole reason we started studying this topic was because, interestingly, with Bernoulli variables, so we studied this in the probability context first of all. So it is known that computing this with independence, computing certain functions is easy. And also computing this concave closure for certain functions is easy. So I said it's NP hard, but that doesn't mean there are no instances where it's easy, right? So there are some instances. So we wanted to see whether in those instances, in between these two extremes of dependence and independence, is there a position, like for example, pairwise independence is in between, can it be easy there also? That was the actually thought with which we started off, but we ended up getting, quite, we got many more results. Yeah, so this pairwise independent extension here is exactly, now you can see the concave closure plus this one extra constraint. That's all is the extra one. Right? So that's why we put an F plus plus here. Right? Everything else is the same, except that there is this additional constraint over here. Right? So now, the point is, first of all, I'm not sure why, I don't know how to cancel this at the bottom, but this, you can see that the multilinear extension is always upper bounded by the pairwise is upper bounded by the concave closure because of the way we are the restrictive assumptions. Okay. Now, for the special case where you have a submodular function of this sort, so this is basically nothing but. Oh yeah, it's gone.
No, it's gone, but are you able to access?
Yeah, I'm able to access it. Okay. Thanks. So
you can take 10 minutes, like including discussions.
sure. Okay. I think I will. Yeah. So you can have. Yeah.
Yeah, discussions are anyways going
It
on.
will not be more than I think 10
Yeah.
minutes.
Yeah.
Should be fine. If there are, maybe we could have interactive even before.
Yeah, it's anyways, it's interactive only. Yeah.
Yeah,
So
thanks.
we won't have a dedicated discussion slot, so we'll
Sure.
just take another
Thanks,
10
thanks.
minutes or so.
So yeah, so for the special case of this function which you see here, this is nothing but the max of n random variables, Bernoulli random variables you could think of for the time being. So min of the cardinality of S and 1 is nothing but max C1, C2, C3 all the way up to Cn. And this is basically a submodular function, and as I mentioned earlier, the expectation of this gives you the union probability. So one of my results in the thesis was to get bounds on these type of functions in expectation with pairwise independence assumptions. So that's going to come slightly later, but here you can see f plus x will be the Boole's union bound, which we all are familiar with. It's basically the minimum of the sum of the probabilities and 1. And the multilinear extension will be basically the probability that at least one event happens, the 1 minus the probability of no event occurring, right? Now, what we showed in our work, which recently got accepted at Sam Journal of Discrete Mathematics, was that even f plus plus x can be computed for this specific function in a closed form. So this was quite surprising actually, because pairwise independence was thought of, at least by and large, to be a hard problem, because as I mentioned, you deal with a lot of distributions. But it so happens that for this specific function, you can actually get it in a closed form. As you can see, the difference between Boole's bound and this, there is just this extra one term here, minus xn times the sum of the first n minus 1 probabilities. So this is assuming that the probabilities are ordered like this. So you can see this is a better bound than the Boole's bound because of the the pairwise independence assumption. Right? It's a better upper bound. Anyways, so the point what we showed actually in our work was that just like this first result, which I showed was of Shipra Agrawal a few slides back, f plus by capital F is less than e by e minus 1 was shown by them. And what we did was, if you replace capital F by f plus plus, you can actually improve this bound to 4 by 3. Now, for which function? For this specific function. So this was also part of the paper which was in sigma. So now, it's interesting because what it says is, if you relax your assumptions from complete independence to pairwise independence, you will end up coming closer to f plus x, the concave closure. Why? Because the concave closure assumes nothing literally except the margins. Pairwise independence assumes a little bit. Pairwise independence is also uncorrelated, but it's not as restrictive as mutual independence. So because you're making your restrictions lesser, you end up coming closer to the f plus x. So 4 by 3 is a better bound. 4 by 3 is much better than e by e minus 1. And also this is happening because submodularity as such encourages negative dependence. The whole idea of submodularity is negative dependence, right? As we saw in the coffee and tea example, for example, right? It's better that they're apart than they're together. So because submodularity encourages negative dependence, and so this f plus x over here, this Boole's bound is a perfect negative dependence. Boole's bound exactly gives you perfect negative dependence. So therefore, f plus plus x will be expected to be closer to f plus x than this f of x, right? Now, it's not that always f plus x is hard to compute and f plus plus is easy. Actually, both are hard problems. Both are NP hard problems. But in some cases, you can do f plus easily. In some cases, you can do f plus plus easily. So whichever is easy, the other one can be approximated using the easy one. So this is now the biggest question in our mind was, okay, this is fine, but does this result generalize to other functions beyond this guy? Right? Because if that happens, that will be pretty interesting, right? Because it's not only this monotone submodular function, but it could generalize. And that set off the whole series of research. So what we were able to show, the good news is it is true for, as we showed just now in the previous slide, it's true for the union of n events, right? So that's the previous slide that we could show. Then we were trying to see now, what if I make it a general submodular function? So please note that this union of events has a lot of symmetry. That's why it was easier to deal with. The moment you make it general submodular functions, you lose the symmetry. So it's not as easy, right? So what happens is, for large n, first of all for small n, but any x, so this vector x can be anything, but I need n to be 2 and 3. Then we can show that it's bounded by 4 by 3 for any submodular function. And the third result which we have, okay, if you want now any number of inputs n, then I will have to reduce the probabilities to a small, in the region of the hypercube where they are small. Okay, and there's we have a theorem in our paper which exactly characterizes this. But the point is, dealing with large dimensions requires somewhere a compromise. And if you're dealing with, large probabilities, then you need a compromise in the dimension space. So now we do suspect that this holds more generally because our numerical results show that it's true for all n and all probabilities and all submodular functions. So there are 3 degrees of freedom here: x, n, and f. So we believe, at least it's a conjecture, that it's true for all of for any of these x and f. But we haven't proved it yet, so that's the next research question.
So you're saying there is no lower bound. It says that, for example, this particular, let's say n is very large, but
Yes.
the probabilities are small. You can't do better than this.
Exactly. So yes, you're right. So what we're saying is that even if n is, if at least the conjecture says, even if you give me large n and even if you give me large probabilities, you basically the bound will be less than 4/3 and not e by e minus 1. So earlier it was e by e minus 1, which is what I think 1.5 something, right? Now this is 1.33. So we are saying that even then, with all these changes, you still will not do worse than 4/3. In other words, you can get at least a 3/4 approximation for for this f plus of x, the concave closure, using this f plus of x. So there are certain extensions. Okay, I think I will just skip these in the interest of time. But yeah, the main ideas are basically that we enumerate the submodular polytope. Okay, so okay, I'll just come. Is that working? Is it? Oh yeah, here it is. So basically, the key idea is that you partition the space of probabilities. Right. So here you can see x1. This is just the simplest case of 2 variables. So you can partition it like this: x1 plus x2 less than 1, greater than 1. And then you can look at the extreme points of the submodular polytope. So what I mean by submodular polytope is the polytope of those functions, the submodular functions, which satisfy monotonicity and submodularity. So it is sufficient to look at the extreme points because essentially we are going to be maximizing, right? So and if as long as we can show that this f plus x, and so we cannot get this exactly for all n, but for n equal to 2 we can get this exactly, and they are linear in f, so therefore it is sufficient to look at the extreme points of f. N equal to 3 it becomes more complicated because here if you look at these masses x1, x2, this is the joint distribution basically, right? It is oblivious to the function. You give me any function in this space, I can give you this exactly the same extremal distributions. But the moment you go to n equal to 3, this doesn't work. That means the moment in n equal to 3, if you change this guy, then these distributions will also change. And that makes things very messy. And therefore in n equal to 3, we had to do a lot more of analysis, which I will not go into now. But I just mentioned the point. So you see like here, the moment you change this is the submodular function, there you can see the values here. The moment you go from here to here, you can see there is a change in the f plus and the f plus space. So this makes things complicated, but we are able to do more complex partitioning of the of the probability space, and we are able to actually prove the result for n equal to 3. Right, and then the other result was this: that if you increase the dimensions, but if you keep the probabilities satisfying this, right? So that is the sum of the smallest n minus 1 probability is less than 1, and the largest probability is less than 1/4. We can still show this. Right? So these are some results which we have. So let me just conclude. I'm not going into these details, but this is our conjecture. This is it's true for all submodular functions for all x and for all n. But currently we are able to prove it only for these 3. And the numerical evidence, we tried a lot of submodular functions. Some of these are written here. And we were till now unable to find a single instance where the 4/3 bound was beaten. So, and it so happens that actually the 4/3 bound is attained with the simplest of functions, like the function which I showed you, the union bound function. That's the function which attains the 4/3 bound. The rest, the complicated functions are all giving us much better bounds than 4/3, which means something like close to 1, 1.2, not even. So it's interesting that at the end of the day, it seems like the result, and this is true even with the earlier result of e by e minus 1. What Shipra proved was that e by e minus 1 is attained by this same union bound function. It's not a complicated function. So it seems that at the end of the day, it's at these simple functions which are actually giving us the best results. So that also encourages us that probably it's not too hard to prove the result for the other functions. So with this, let me thank you all for your patience, and yeah, look forward if there's time for any questions. Otherwise,
Yeah, we are almost around 4. So if there are any questions, maybe we can take one-to-one and the meeting we can conclude. So yeah, I mean, thank you for the presentation, Arjun.